Hello everybody, welcome into another lesson. So today we're going to do some more trigonometry. This is lesson 2 out of 3 of some trigonometry with right triangles. So yesterday we talked about the tangent ratio. Today we're going to talk about the sine and cosine ratios. So up first again here we have our right triangle where you see angle A. You have your adjacent leg, you have the opposite leg, and you have the hypotenuse. Well, we have here the sine ratio. If you want to find the sine of angle A, it's the ratio of the opposite leg to the hypotenuse. And it's going to be abbreviated, it looks like sin A. That's how it's abbreviated, and that's what we're going to use today. And going forward in the future, it's equal to opposite over hypotenuse. If you want to remember sine, remember the acronym SOH. Sine, opposite over hypotenuse, for SOH. So that's the sine ratio. And then we're going to talk about the cosine ratio, which is sort of similar, but it's a little bit different. All right. Okay, and then we use the same right triangle. Again, you have angle A, you have your adjacent leg, your opposite leg, and your hypotenuse. We have the cosine ratio here. So to find the cosine of angle A, it's going to be the ratio of the adjacent leg to the hypotenuse, which is abbreviated cos A. That's how cosine's abbreviated, equal to adjacent over hypotenuse. If you want to remember cosine, remember CAH, C-A-H, which would be cosine adjacent over hypotenuse, so CAH. So we've now learned the three ratios. We've learned tangent, we've learned sine and cosine. I'm going to give you a helpful acronym to remember all three. If you can remember SOH CAH TOA, SOH CAH TOA, if you can remember that acronym, you'll remember the three trig ratios. SOH CAH TOA, for SOH you have sine is opposite over hypotenuse, CAH for cosine is adjacent over hypotenuse, and then TOA for tangent is opposite over adjacent. If you can remember SOH CAH TOA, you'll remember the three trig functions that we've talked about. And now let's do some examples of such. We're going to do some similar exercises to yesterday's. They'll be very similar, only we're going to be doing the other functions today. We're not going to do tangent at all today. We're going to do sine and cosine. Okay, so we want to find the values of x and y. We have the value of the hypotenuse being 35. Well, let's start with x first. We want to find x. Well, we have a 37-degree angle in this right triangle. Opposite the 37-degree angle is x, then you have the hypotenuse. If it's going to be opposite over hypotenuse, you're going to use the sine ratio. So you would take the sine of 37 degrees, set that equal to your opposite side of x over your hypotenuse of 35. And then to solve for x, multiply both sides by 35. You would get x is equal to 35 times the sine of 37 degrees. Which then we're going to do a 2 decimal place approximation to get the answer. Now, when you go into your calculator, just like yesterday's lesson, make sure it's in degree mode. If your calculator says this, that means it's in radians. Now, let me put it this way. If your calculator shows a button that says rad, R-A-D, that means radians, so you're already in degrees, so you're good. Then you can leave it alone because it's already in degrees. If your calculator shows a button that says that for degree, it means you're currently in radians and you need to hit that button in order to switch it to degrees. Because if you use radians, you're going to get a completely different result, which will skew the results. So let's go ahead now and find this value. So 35 times the sine of 37 to 2 decimal places is approximately 21.06. So the value of x is approximately 21.06. Now, we've solved for x, we need to solve for y. Well, if we notice here we have the 37 degree angle, y is the adjacent leg to 37, and then we have the hypotenuse 35. Since you have an adjacent and a hypotenuse, you're going to use the cosine ratio. So you would set up your ratio as the cosine of 37 degrees is equal to y over 35, which then y would equal 35 times the cosine of 37 degrees. And then we'll do a 2 decimal place approximation for this. And then again, make sure your calculator's in degree mode, not in radians. So we'll take 37 times the cosine of 37 degrees, which would give you about 27.95. So y has a value of approximately 27.95. And that's how you would solve for these missing values. All right. Another right triangle, but it's a little bit tilted. We have a 58 degree angle here. We have y, we have x, and then we have 120 for the length of the hypotenuse. So we need to solve for x and y. Well, good place to start is x. We notice that x is the opposite leg from the 58 degree angle. Then you have the length of the hypotenuse. Opposite and hypotenuse would be the sine ratio. So set up your sine ratio. This would be the sine of 58 degrees is equal to the length of the opposite leg, which would be x, over the length of the hypotenuse, which would be 120. And then, of course, x would equal 120 times the sine of 58 degrees. And now let's do the decimal approximation of that. So let's go ahead here, let's do that. Will give you about 101.77. So x has a length of approximately 101.77. So we solve for x, now we need to solve for y. we have our 58-degree angle again. Well, the leg with a length of y is the adjacent leg to 58, and then you have the hypotenuse. If you have adjacent and hypotenuse, you're going to set up a cosine ratio. So this time we'll take the cosine of 58 degrees. We'll set that equal to the adjacent leg with length y over the hypotenuse, which is 120. So then y would equal 120 times the cosine of 58 degrees. And then we'll just put the value into the calculator and get a 2 decimal place approximation. So let's see here. We have 120 times the cosine of 58, which would give you about 63.59. So y is approximately equal to 63.59. All right. Well, that's a right triangle. That's okay. We'll leave that alone. 50-degree angle. Y, X, and then the leg is 75. Now, here's a fun one. This time, we don't know the length of the hypotenuse, that's y. We don't know the length of this one leg, that's x, but we know the length of the adjacent leg, 75, to this 50-degree angle. Well, to solve for x, we're actually going to want to relate the opposite over the adjacent, which would actually bring in the tangent. We're going to use the tangent function for that. So set up your tangent ratio. The tangent of 50 degrees is equal to x, which would be the opposite leg, over the length of the adjacent, which is 75. So then x would give you 75 times the tangent of 50 degrees. And then we'll just do our 3 decimal place approximation. Which would give you about 89.38. So x is approximately equal to 89.38. So we found that using the tangent function. Now we need to solve for y. Well, you have the adjacent leg here, 75, the hypotenuse y. If you're relating the adjacent and the hypotenuse, that's going to be the cosine ratio. So you'll set up the cosine of 50 degrees is equal to the adjacent leg of 75 over the hypotenuse of y, which would then give you y cosine of 50 degrees equals 75, which would then give you that y is equal to 75 divided by the cosine of 50 degrees. And then we'll do the decimal approximation and we'll get the value for y, for the hypotenuse. So this will be fun. Which would give you about 116.68. So the length of the hypotenuse with length y is approximately equal to 116.68. let's see what we got here now. Another right triangle. X, Y. This is 40 degrees. We got the hypotenuse with length 80. So again, we're going to solve for X and Y. Notice we have a right angle with a 40 degree acute angle. We have the hypotenuse with length 80. We got to find the two legs. Let's solve for X first. X, of course, is the opposite leg from the 40 degree angle. Then you have the hypotenuse. Well, opposite over hypotenuse is the sine function, the sine ratio. So set up your sine ratio. This would be sine of 40 degrees is equal to your opposite leg of X over your hypotenuse of 80, which would then have to mean that X equals 80 times the sine of 40 degrees. And then we can get a 2 decimal place approximation. Alright, so 80 sine of 40 gives you about 51.42. So X has a value of approximately 51.42. And now we want to solve for Y. This time the Y is the adjacent leg to the 40 degree angle. Then we have the length of the hypotenuse. If you have adjacent and hypotenuse, you're going to use the cosine ratio. So set up your cosine of 40 degree ratio. That would equal your adjacent leg of Y over your hypotenuse of 80, which Y would then equal 80 times the cosine of 40 degrees, which will now do a decimal approximation for this. Which would give you about 61.28. So Y has a length of approximately 61.28. All right. Interesting one here. Alright, so we notice here, before we even proceed to finding the lengths of X and Y, you have both sides of this whole triangle. If you take these two right triangles, combine them into one, you have an isosceles triangle, both with lengths 30, right? Well, this angle here is 70, so that means the other angle has to also be 70 by the isosceles triangle theorem. Now we're set up. Now we can proceed to find X and Y. Let's solve for X. Well, X would be the opposite leg, then we have the hypotenuse. So if you relate the opposite leg and the hypotenuse, that's going to be the sine ratio. So take your sine of 70 degrees, set that equal to X over 30, which then means that X would be equal to 30 times the sine of 70 degrees. Then we should be able to get a 2 decimal place approximation here. which would give you about 28.19. So the value of x is approximately equal to 28.19. Now we just need to find y. Well, in this right triangle, y is the adjacent leg to the 70-degree angle. Then we have the hypotenuse. If you relate adjacent and hypotenuse, you'll do the cosine ratio. So set up the cosine of 70-degree ratio. That's going to equal the adjacent leg of y over your hypotenuse of 30, which then means that y is equal to 30 times the cosine of 70 degrees. And then we can do another 2 decimal place approximation. Which would give you about 10.26. So the value of y is going to be equal to approximately 10.26. So that was a nice use of the isosceles triangle theorem to get us started. Good one. Okay, so this is interesting here because first we have an isosceles triangle, right? So, because both of these have length x, and you have a 65-degree angle here across from the 1x, that means this angle also has to be 65 degrees by the isosceles triangle theorem. And there's something else. Now, we notice in each of these right triangles you have that both a hypotenuse and a leg congruent, so they're actually congruent by the HL theorem. So I'll mark these two bottom legs of each being congruent because corresponding parts of congruent triangles are congruent. Now, if the length of this whole bottom base here of the major triangle is 24, and you have two congruent segments here that make up that the base of the big triangle, that means it splits that 24 evenly into two 12s. So now we know the length of each of the bottom legs of the two smaller right triangles. Now we can go ahead and start solving. Let's solve for x first. So if we want to solve for x, we're going to, of course, we have 65-degree angles. We take the adjacent over the hypotenuse. So set up your cosine ratio for 65 degrees to solve for x. That equals the adjacent, which is 12, over the hypotenuse of x, which would then give you x cosine of 65 degrees equals 12, which would then give you that x is equal to 12 divided by the cosine of 65 degrees, at which point then we should be able to get a 2 decimal place approximation to this. So let's take 12, divide that by the cosine of 65. That give you approximately 28.39. So x is approximately equal to 28.39. Now we need to solve for y. Again, you have your two right triangles, but this time y is the opposite leg to the 65-degree angle. Then you have the adjacent leg, which is 12, opposite over adjacent, that means tangent. So set up your tangent ratio of the 65 degrees. That's going to equal the opposite leg of y over the adjacent leg of 12, which means that y is equal to 12 times the tangent of 65 degrees. And then we can do a 2 decimal place approximation. Which would give you about 25.73. So x has a value of approximately 28.39. Y is approximately equal to 25.73. All right. What do we got now? Oh, good one. This is different now. We're shifting gears a little bit. You're going to see how in just a minute. So this time we have a right triangle. We're given the length of the opposite leg from this angle and the hypotenuse. We just don't know what the value of the angle is. This is where inverse trigonometry functions come into play. Well, if you have an opposite angle over hypotenuse, that's going to be a sine. So you're still going to set up the sine of v degrees. You'll set that equal to 22 over 50. Now, remember how we did inverse tangent or arctangent on your calculator yesterday? It's going to be the same with sine. You're either going to see one of two buttons on your calculator. You'll either see sine inverse or you'll see arc sine. Both mean the same thing, sine inverse or arc sine. So in order to find v degrees, you're going to take the sine inverse of both sides. Which sine inverse of the sine function just leaves the value inside the function, which would just be v. And then we're going to round this result to the nearest degree. Again, make sure your calculators are set to degree mode so you get an answer in degrees. You don't want an answer in radians. That would give you approximately 26 degrees. So when you take the inverse sine function or the arc sine function, the value of v is approximately equal to 26 degrees. So yes, that was a good example there of using inverse functions. So we've learned about arctangent and then now arcsine. I know there will be examples of arccosine. I have no doubt about that. In fact, I'm pretty sure the next one is. All right, what do we have here? This angle up here is V degrees. The length of this leg's 11. The length of the hypotenuse is 28. So again, we know the length of the adjacent leg to V degrees to be 11. We know the length of the hypotenuse to be 28. If you're dealing with adjacent and hypotenuse, you're going to set up a cosine ratio. We just don't know the value of V degrees. Nonetheless, we'll set up the cosine of V degrees is equal to the length of the adjacent leg of 11 over the hypotenuse being 28. And then, yes, you guessed it, you're either going to, on your calculator, you're going to end up using the cosine inverse, the cosine to the -1, or arc cosine, depending upon what your calculator says. In order to get V by itself, we need to take the inverse cosine of the cosine of V, set that equal to the cosine inverse of 11 over 28. This, of course, would turn into cosine inverse of cosine cancels out the trig. You just get the V degrees. We're going to round the value of V to the nearest degree. So let's take the cosine inverse of 11 over 28. Again, make sure your calculator's set for degree mode. That would give you about 67 degrees. So V is approximately equal to 67 degrees. Very interesting one. Okay, so this time we have the value of, we need to find the value of a length and a degree. We have the hypotenuse of both right triangles being 10. The length of the whole base of the one triangle that these two together form is 9. Well, we need to establish something here first. A couple things, actually. Wouldn't this be an isosceles triangle, the whole triangle together then, because both of these sides have a length of 10, which would mean this angle here is also V degrees, which means the hypotenuse and the leg are congruent of each right triangle, so therefore these two right triangles are congruent to each other. Which means the bases of both right triangles, the bottom legs, are congruent to each other by corresponding parts of congruent triangles are congruent. If the length of this whole base is 9, split into two congruent segments, that has to mean that each of the bottom legs of the right triangles have a length of 4.5. Okay, so we've established that. Now, we can go on to solve for V degrees. We're going to need to solve for V. So, to do that, of course, we have the adjacent leg and then the hypotenuse, which means we're going to need to set up a cosine ratio. So, we'll set up the cosine of V degrees. That'll be equal to the adjacent leg of 4.5 over 10. which then if you take the inverse cosine of both sides, you'll have v is equal to the cosine inverse of 4.5 divided by 10. And then we'll get a decimal approximation for, we'll get a answer to the nearest degree for this value here. So find the cosine inverse of 4.5 divided by 10. That would be about 63 degrees. So the value of v is approximately 63 degrees. Why don't we do ourselves a favor, go ahead and write that in here now for where v was, because that's going to help us to be able to get an approximation for x, which is the length we need to solve for. Now, there are two ways we can solve for x. One way is to take the tangent of 63 degrees, which would be x over 4.5, or we could take the sine of 63 degrees, which would be x over 10. Since we're dealing with the new stuff today, let's do the sine. So if we take the sine of 63 degrees, that would be equal to the opposite leg of x over the hypotenuse of 10, which then means that x equals 10 times the sine of 63 degrees. Then we should get a decimal approximation for x. Which would be about 8.91. So the length of x is approximately 8.91. Now let's say we went the tangent route. If we did the tangent of 63 degrees, that'd be equal to the opposite leg of x over the adjacent leg of 4.5, which would have to mean that x is equal to 4.5 times the tangent of 63 degrees. And we should get approximately the same result we got when we did the sine. So let's go ahead and find that real quick. Yeah, we get about the same result. So you actually get about 8.83, but sometimes they're not exact, they're in the ballpark, but these are pretty much in the ballpark from each other. So you get roughly 8.9 if you're rounding to the, if you're rounding up to the nearest tenth or down to the nearest tenth. You get approximately 9 if you round to the nearest number. So they're not always 100% exact, but you should be in the ballpark if you choose either one. All right. I have 3 more exercises, then we're done for the day. Okay, so we have another one where we have a big triangle split into two right triangles, okay? Well, we know the length of the hypotenuse of each of the right triangles, but we know the length of the whole side here of the top base is 16, but we need to find x and then the v degrees. Well, observe right away, if you consider the whole triangle, this is an isosceles triangle because you have this side length of 12, this side length of 12. So right away we notice we have the hypotenuse of both right triangles congruent, and obviously this leg's congruent. Therefore these two right triangles are congruent, which then is going to mean, if they're congruent, that these two legs of the right triangle, which make up the whole base here for length 16, are congruent. If you have 16 split into two congruent parts, that's 8 for each part. So now we have the length of a leg and the hypotenuse. Well, it sounds to me that first we need to solve for the degrees, right? That's what we should do first. Solve for the v degrees. Well, the side opposite v degrees has length of 8, the hypotenuse has length 12. So if you have opposite over hypotenuse, you're going to do a sine ratio. So you'll take sine of v degrees, set that equal to the opposite side of 8 over 12. Take your sine inverse, v would be equal to the sine inverse of 8 over 12. And then we'll get a approximation to the nearest degree for that sine inverse. Which would be about 42 degrees. So V is approximately equal to 42 degrees. So now why don't we put that in here, because that's going to enable us to solve for the x. Now let's go ahead and solve for x here. We notice that the length of x, that leg is adjacent to the 42 degree angle, and then we have the hypotenuse with a length of 12. Adjacent and hypotenuse would be cosine. So we'll take the cosine of 42 degrees, we'll set that equal to x over 12, which means that x is equal to 12 times the cosine of 42 degrees. Then we should get a 2 decimal place approximation for the value of x. Which would give you about 8.92. So x is approximately equal to 8.92. We could also have gone the tangent route and said that you would have the tangent of 42 equal to 8 over x, and then done it that way. You should get a number in the ballpark of this for x. Probably not the exact same number, but it should at least be in the ballpark. So, your pick. Trigonometry can leave room for different approaches of how to solve the same problem. I think you'll find that. 2 more problems here. Let's see what we get this time. Okay, so interesting. We don't right away have a right triangle. We have a triangle with two V degree angles and then one W degree angle. We have one leg here with length 10, and then the length of the whole base is 16. Well, one thing that's going to help us here is that we have an isosceles triangle because this angle's V and this angle's V. Across from this V angle is 10, so that means this side also has to be 10. So that's going to help us immensely. Now, next thing for us to do is form an auxiliary line and form two right triangles. So let's go ahead and do that here. So we'll have two right triangles here. Now notice, we form these two right triangles. We have the hypotenuse of each is congruent, and then since they share this same leg, we have a leg congruent. So therefore these two right triangles are congruent to each other, which would then leave that the two bases here adjacent to the V degrees are also congruent since they're corresponding parts of congruent triangles. If you have 16 split into two even pieces, that's going to be 8 apiece. So now we know the length of one of the legs. So, next thing we're going to do is find V. Now, if we consider here, adjacent to V, we have 8, and then the hypotenuse is 10. So adjacent and hypotenuse, you'd be setting yourself up for a cosine function. So the cosine of V degrees is equal to that 8 over 10, which means the cosine inverse of this would just have V equal to the cosine inverse of 8 over 10. Then we should get an approximate degree value for V. So let's go ahead and find the cosine inverse of 8 divided by 10. That'd be about 37 degrees. So V is approximately equal to 37 degrees, right? Well, we still have to find the degrees of W, but that's not going to be too bad. In fact, we don't even need to do any trig for that, because if you consider the whole triangle, you have V, V, and W. We know that the sum of the interior angles of a triangle equals 180. So we could take V degrees plus V degrees plus W degrees, set that equal to 180 degrees, which would give you 2V plus W equals 180 degrees. So then you would take 2 times your 37 plus W. That would equal 180 degrees. 2 times 37 is 74, so you'd have W plus 74 equal to 180 degrees, which would make W approximately equal to 106 degrees. So the value of W is approximately equal to 106 degrees, and I say approximately because V was also an approximation. These wouldn't quite be exact, but they're approximately right, 37 and 106. Alright, that just leaves one more problem then. We just got one more. Let's see what we get this time. This is 30 degrees. This is 75 degrees. This is 20. Then we have X and Y. So we'll be finding the length of sides. All right. Well, whoops, I better put degrees here. Okay, well, before we even go any further, do we notice here, if you add 30 and 75, what do you get? 105. If you take 105 away from 180, you would get that this angle is also 75. So now that you have two of the same angle, that means you actually have an isosceles triangle. So that means that X would also have to be 20. So since you have an isosceles triangle, X equals 20. We didn't even need any trig to find that. Now Y, that's going to be a different story. So once you've established your angles, you can go ahead and draw an auxiliary line to form two right triangles, which will probably go this way, since we're working sideways. I think it's important to preface this that the length of this whole side is Y. Right? Okay, so here's something though. You have the hypotenuse of each right triangle and a leg congruent, so therefore these two right triangles are congruent, which means these two legs are also congruent. If Y is split into two pieces, then half of Y is what the length of each of these segments would be, is half of Y. So now we're actually getting fractions involved. Okay. Now, we have here, we know X is 20. And then, which is the hypotenuse, and then we have the adjacent leg to 75 being half of Y. So you're going to set up your cosine ratio since you have adjacent. So take the cosine of 75 degrees, that's going to be equal to your adjacent leg of half Y all over your hypotenuse of 20, which then means now you should get that half of Y is equal to 20 times the cosine of 75 degrees, which if we want to just solve for Y outright, which is what we want to do, you need to multiply both sides by 2. You would get that Y is equal to 40 times the cosine of 75 degrees. And then now we can proceed to get our decimal approximation here to 2 decimal places. So let's go ahead and do just that. 40 times the cosine of 75, so that would give you about 10.35. So Y is approximately equal to 10.35. And that's it for today's lesson. I did put that in, right? Yeah, I sure did. Alright, yeah, 10.35. I guess I just didn't draw it to scale very well, but yeah. Okay, so that's it. Next lesson, we're going to talk about some applications of these trigonometry functions. We'll have some word problems with it and show you some real-life applications of this. So I hope everyone has a great day. Take care.